patterns predicted by particles which had been seen. We started to perform the experiment in earnest in November of 1963. In fact, we started tuning the beam round the clock, 24 hours a day. It certainly wasn't smooth sailing. We had many difficulties, technical. The lineup of the beam had to be constantly checked, magnets constantly tuned. The chamber had minor difficulties, leaks. But finally, we persevered, worked very hard, 24 hours round the clock, until in January we were able to start taking a few Ks per picture, 1 to 2 Ks. We worked a little bit harder. We finally were able to get it to 3 to 4 Ks per picture. And by late January, we were taking 2,000 pictures a roll, a few rolls a day. So finally, we were able to attain something of the order of 100,000 pictures. Of course, as soon as we had these pictures, we started scanning them. Again, looking for these patterns. We scanned 10, 20, 30,000, still no omega. Finally, we went to roll 53, and picture number 97,025. That number stays in everyone's mind around here. And finally, we found the omega. And here's a photograph of the omega. The pattern, very similar to the pattern I had shown you before. The strangeness -1, the strangeness -2, and the strangeness 0 particles. And this little particle, this little 3-centimeter particle, this was the omega. The omega we spent months, years looking for. We were exuberant. I mean, the Friday that it was found, we just stood around looking at each other, a bit numb at the beginning. Then finally, everyone broke out into smiles, and someone started to do a dance. It was very happy. In fact, in our exuberance, we just completely neglected to call Murray Gell-Mann in California. In fact, he had to call us when he found out about it. But it was a very peculiar feeling. It seems to make it all worthwhile, this 1 to 2 years effort. You sort of stand around, a few of us, and you say, at this moment, we few on the face of the earth, we're the only ones who know that this particle, this omega that goes this short distance, this particle exists. Other people may think they know. Gell-Mann probably thought he knew, but he didn't know. We knew.
That, then, is the story of the omega minus. What does it mean? What is the significance of the fact that nature seems to obey this rule? I think today nobody knows. We'll only know, really, when we completely understand, or more completely understand, the fundamental laws of interaction of the nuclear particles. And this is a vital step forward to that understanding. But it isn't the understanding itself. And until we get that, we'll not really know the meaning of this, the fact that nature seems to obey the rules guessed at by Gell-Mann and Feynman. It's analogous to the discovery of the periodic table by Mendeleev a century ago. He discovered at that time that various chemical elements came in families and that there were relations among them, that the chemistry of sodium and potassium, for example, were similar. This was extremely important in the development of science and in bringing about the ultimate understanding of the behavior of atoms. But the real understanding of the reason why sodium and potassium was similar, why the periodicities among the chemistry, in the chemistry of the various elements existed, could only come with the 50 years later with the knowledge of atomic physics. And this knowledge required a complete transformation of ideas about nature, a complete change of the philosophical position. Ideas that were impossible to appreciate at the time of Mendeleev. The principle of uncertainty of Heisenberg had to be discovered. The whole understanding of the relation of cause and effect had to be modified with the principle of indeterminacy. And so it's going to be here. We will not understand really how nature makes this rule until we understand the nuclear interactions, and we won't understand those, I'm sure, without a deep and profound transformation of ideas somewhere along the line. We already see some of the difficulties. This law of Gell-Mann and Feynman, this symmetry law, is not a perfect symmetry. If it were, the statement would be that the replacement of one particle by another will make no change. For example, the replacement of a neutron by a lambda should make no change. And yet the neutron and lambda differ in mass alone by some 20%. So there alone is a change that when you take a neutron and replace it by a lambda, the mass is different. So this symmetry is not perfect. It's an imperfect symmetry. Physicists are happy with a perfect symmetry. To say something is absolutely true and absolutely symmetrical seems to be a succinct, simple, and elegant statement of a law of nature. If a thing were completely unsymmetrical, then there would be nothing to say. But by what kind of a view is a thing that is only partly symmetrical natural? Is a thing that is only partly symmetrical beautiful? Well, the artists say that in this camellia bush here, the artists feel that the camellia, in its partial but near symmetry, is especially beautiful, and far more beautiful than a perfect geometrical pattern. But physicists feel that a partial symmetry is an indication that some deeper and more profound description of nature is possible, that there's gold in them thar hills. So we got a peculiar thought to grapple with, this partial symmetry. We're kind of stuck. We need a new idea. Before we'll really get the nuclear forces understood, some great new idea is required. Looking for symmetry is an old one. Poincaré suggested it. Einstein used it. Really came into its own when quantum mechanics was developed. But all the information that we're accumulating, the places where we're really getting stuck, understanding the relation of these particles, is somewhere where we're missing some important, great idea. We have some prejudice that's in our way. That's the way it always is in these pinnacle discoveries. The big pileup of stuff, all the old things that you've thought of before, you try again and again. But the great discovery always involves a great philosophical surprise. The pinnacle discovery isn't so much a fact as that it's possible to look at nature in a thoroughgoingly different idea. How strange it is, listen to this. How much is known after 200 years of studying physics? How much is known about the electrons, light, everything? And in order to understand the nuclear forces, it's almost certain that we're going to have to take a completely different view about everything that we know already, philosophically that is. We're going to have to find another way to look at the world in which everything that we've already found out about it is the way it is. And yet that little detail about what goes on in the nucleus then falls into place. It's a very hard job. It's lots of work. So what do we do it for? Because of the excitement, because of the fact that each time we get one of these things, we have a terrific El Dorado. We have a wonderful new view of nature. We see the ingenuity, if I may put it that way, of nature herself, the peculiarity of the way she works. It takes a terrible strain on the mind to understand these things, and the real value of the development of the science in this connection, or I mean the thing that makes me go on, is this, the difficulty of understanding it. That these apes stand around and look at nature and find that to really catch on, they have to polish their mind to the very last. We live in a heroic age. We live in a moment that'll never come again. These discoveries cannot be made twice. One doesn't discover America 2 or 3 times in succession, really. And one doesn't discover the laws of nuclear forces or electricity more than once. Some people say our age is meaningless. Those are only people who don't know what we're doing in this age. That this age is the age in which mankind is finding out about the nature that he lives in. And if they don't understand what's already been uncovered, they can't appreciate the search. What makes us so sure that the new discovery of the interrelationship between nuclear forces is going to be so wonderful? How do we know it isn't going to be some complicated, dirty, or simple thing? We don't know, but we keep on trying anyway. We're not sure. It's worth the risk, because it very likely will be peculiar, and if it is, it'll be very interesting. How long is it going to take? Do we have all the clues? Every time there's been a very great discovery, one could look back and say, Why didn't we think of that before? Of course, there's a time so far before that you say, well, the reason they didn't think of it, they didn't have enough facts from experiment. Question. Do we have enough facts from experiment so that after this thing is discovered, people look back and say, why didn't they think of that before? How far before? In 1964. My colleagues don't agree with me, but I think this is the day. I think that we now know enough that if with a sufficiently clear reasoning, we could come to the answer. Or put it another way, when we do finally find the answer after the experiments have given us too many clues, a lot of extra clues, we'll look back and we'll see how a perfectly sensible, logical line of reasoning from the present position could have brought us to the understanding. I wouldn't have said that before the discovery of the omega minus. That, to me, is the significance of this discovery.
Thank you.